In this video, you will incorporate hysys-based heat exchanger rating calculations into an existing heat exchanger model. You will also follow the workflow to use Aspen shell and tube exchanger via Aspen exchanger design and rating to rigorously design and simulate a shell and tube heat exchanger. In this video, the refrigerated gas plant flow sheet you constructed earlier used the simple weighted heat exchanger design model to represent the gas-gas heat exchanger. By incorporating exchanger size and geometry into the calculation, we can rate an existing exchanger and determine how it might perform within that process. We can even go a step further with the convenient linkage between Aspen hysys and the Aspen exchanger design and rating, EDR, and size an actual heat exchanger based on known process conditions and physical properties. This video includes the following tasks: review weighted model, apply a rating model, integrate EDR calculations. Task 1. Review weighted model. In a previous video, the gas-gas heat exchanger in the refrigerated gas plant simulation was set up to solve using a fixed minimum approach temperature specification. The simple weighted model, however, allows you to fix any desired operating specification. You will start the task by exploring other possible operating specifications for the gas-gas exchanger, and then preparing the flow sheet to perform a heat exchanger rating calculation. Check the UA value of the gas-gas heat exchanger. Using the Worksheet tab, record the temperatures of streams, gas to chiller, and sales gas. Now navigate to the Design tab and on Specs page, deactivate the temperature approach and activate the UA. And now specify a value of 15,190 for the UA. Unlike the simple endpoint and weighted design models, the detailed dynamic rating model in Aspen hysys uses heat exchanger geometry and sizing information to estimate the heat transfer coefficients as well as shell and tube side pressure drops. These parameters are then used to determine the outlet conditions for the heat exchanger. This approach requires both feed streams to be fully defined in order for the exchanger to solve, something that is not mandated for simple endpoint or simple weighted case. This requirement necessitates some changes in the flow sheet in order to use a rating model. Specifically, a recycle is often used to ensure all heat conditions are known prior to solving the heat exchanger. Add a new material stream. Name it Recycle Out. Click Define from Stream. Select LTS Vapor at the source stream. This will transfer all data into the new stream. Now break the connection between the material stream LTS Vapor and the gas-gas exchanger. Connect the new stream Recycle Out to the gas-gas exchanger as the shell side outlet. Add the recycle operation to your flow sheet. Set the inlet stream to LTS Vapor and outlet stream to recycle out. At this point, the gas-gas exchanger should have enough information to solve. Task 2. Apply a rating model. Let's assume you are asked to find a heat exchanger that will serve as the gas-gas exchanger. However, since you are on a very strict budget, you can only consider used equipment. A heat exchanger has been found in the surplus supply of a nearby plant. The critical process parameter to maintain is a sales gas stream temperature of 0 degrees centigrade at the minimum. You need to determine if this heat exchanger can be used for the gas-gas exchanger. The surplus exchanger has been thoroughly cleaned, so you can assume it to be unfouled. Open the gas-gas exchanger. On the parameters page, delete the tube side delta P and the shell side delta P and the overall UV values. These parameters will be calculated after you switch to the rating model and it solves. Now change the heat exchanger model to dynamic rating. Move to the rating tab and on the parameters page, select the detail radio button. This activates the detailed dynamic rating model and will allow the gas-gas exchanger to begin solving. You will see the program solve because it takes all the default parameters. Heat exchanger sizing information for the hysys-based rating models are entered on the sizing page. On this page, you can configure some overall orientation items for the shell and tube heat exchanger geometry. Change the thema type to BEM. And leave all other parameters at their defaults. Toggle between shell sizing data and tube sizing data to enter the geometry specification for each side. Set the number of tubes per shell to 300. Enter a value of 30 millimeters for the tube pitch. Change the shell buckle type to double and shell buckle orientation to vertical. Set the buckle cut to 15% and enter a value of 100 millimeters for the buckle spacing. Now toggle to the tube side. Enter a value of 3 meters for the tube length. Please note that the rating models in Aspen hysys use generalized correlations for heat exchanger coefficients and pressure drop. These correlations are suitable for approximate results in many cases, but may not be valid for every exchanger and do not go into great detail. For more accuracy, a rigorous model using Aspen exchanger design and rating is recommended. Since the exchanger has solved, now let's check the distilled gas stream temperature. The gas temperature is above the 0, which meets the requirement. Now let's assume that previous experience has shown that after about 6 months of operation, the gas-gas heat exchanger becomes fouled. The fouling factor for both shell side and tube side can be approximately as 0.0001. Return to the sizing page of the heat exchanger. On shell sizing data, change the fouling factor. And on the tube sizing data, change the fouling factor as well. Now let's recheck the cell's gas temperature. We can see that the temperature is below zero, which doesn't meet the requirement. Task 3. Integrate EDR calculations. Since the heat exchanger investigated in Task 2 may not be suitable after 6 months of operation, we will use Aspen shell and tube exchanger by Aspen EDR to design a new shell and tube type heat exchanger that will meet our process requirements. Aspen hysys features a built-in link to Aspen EDR that is greatly simplifies and enhance the relationship between a hysys heat exchanger unit operation and the Aspen shell and tube exchanger design program. Starting in Aspen hysys version 8, the shell and tube exchanger program can now be accessed from directly within a hysys heat exchanger with no additional tools required. And after hysys version 8.4, the activation exchanger analysis makes the process even quicker. Change the heat exchanger model of the gas-gas exchanger to simple weighted model. Delete the overall UA. Set the shell side delta P to 7 kilopascal and the tube side to 35 kilopascal. Navigate to the worksheet and enter a temperature of the cell's gas stream of 3 degrees centigrade. The gas-gas heat exchanger is now defined and calculated based upon a desired process condition. The model also contains the stream compositions and physical properties that match up with these conditions. It is this data, conditions, compositions, physical properties, etc., that are required for a rigorous heat exchanger design calculation. So at this point, we can transition on to the rigorous Aspen EDR environment and make use of Aspen shell and tube exchanger. Navigate back to the parameters page on the design tab. Click on size exchanger. Select size interactively and then click on convert. This is the EDR sizing console. The EDR sizing console allows you to adjust and modify various heat exchanger design options prior to running the EDR heat exchanger design calculation. You can define certain geometry and configuration preferences, allow for fouling factors, and maximum allowable pressure drops. After running an initial design, you can further adjust the EDR preferences and produce additional designs. Enter the Aspen EDR program window, save an EDR readable file, or accept the chosen design and return it to your hysys heat exchanger. The goal of the EDR console is to enhance and simplify the linkage between Aspen hysys and various Aspen EDR programs. Please note that the EDR console is also available in the hysys air-cooled heat exchanger. On the Geometry tab of the EDR console, select the baffle type of double segmental and baffle cut orientation of vertical. Select the Process tab and scroll down to the Process input. Set the fouling resistance of both the hot and cold sides. The ADR sizing console now has sufficient input to execute a heat exchanger design calculation. Click the Size button. After the calculation complete, select the Geometry tab, the ADR sizing console, to check the design results. At this point of the heat exchanger design study, we would mostly like further structuralize the design result. We would investigate things like flow distribution, heat transfer coefficients, vibrational concerns, etc. The ADR sizing console enables you to study these and other items by opening a full ADR browser window. For now, we will continue with the current design. To accept the selected heat exchanger geometry and send it back to the gas heat exchanger, select the Accept Design button. This message asking you if you wish to override the existing outlet stream specification to avoid overspecification. Click Yes. When sending the heat exchanger geometry back in hysys, the heat exchanger unit operation will automatically switch into the rigorous shell and tube heat exchanger model. When this model is selected, hysys takes the known process and lit conditions for the exchanger and sends them into the ADR calculation engine. ADR then computes a new outlet stream conditions based on the selected geometry. As a result of this calculation approach, we cannot have any of our former hysys sample weighted model input values present. Things like fixed pressure drops, UA values, outlet stream temperature, etc. should be deleted. hysys will try to remove these for you, but it is helpful to check and make sure these inputs are not still in place and that is the rigorous shell and tube calculation is indeed running. On the parameter page, make sure that there is no specified outlet temperature values are in place. Now check the worksheet tab to know the new calculated sales gas temperature. Click on the rigorous shell and tube tab. Select the results summary page. This page shows some sample heat exchanger and heat transfer data, including the duty, the effective surface area, the effective MTD, the overall clean coefficient, and the overall dirty coefficient. The calculated pressure drop on the shell and tube side, and the allowable pressure drop on both sides, and finally the velocity at both sides. Please note that import-export buttons allow you to bring in a defined ADR file to produce an ADR file with the data from your heat exchanger in hysys. You can use the ADR console to view more detailed results than what can you see in the hysys results summary. This concludes the 8th video of our course. Thank you for watching.